We're tackling the problem minimum falling path sum. Our goal is to try and find this with minimum complexities of on squared time and on squared space. We have to imagine we've been given an n by n array of integers called matrix. We need to find the minimum sum of a falling path through this matrix. Now, to help you with the visualization, LeetCode has provided some helpful examples. A falling path starts from any element in the first row, choosing the next element in the next row, and this can be directly below or diagonally left or right of it. In other words, we start from the top and we can move to the next element, whether it's down and to the left, straight down, or down and to the right from our current position. Our task is to determine the minimum sum we can obtain falling through the grid by choosing a falling path, either going down, down and left, or down and right each time. As you can see in example 1, there are two possible ways to achieve a result of 13, which is the minimum falling path sum through this grid, both of which start at the middle value in the top row. In the second example, there's only one path, which gives us a minimum falling sum of negative 59. There's no smaller path through the matrix other than that. So, I hope you know what you're doing. Our task is to determine the minimum sum we can obtain by choosing a falling path through our grid. There are four possible methods you can use to do this. You have A, greedy, B, backtracking, C, DFS, or D, recursion plus memoization. I'm going to pause for a couple of seconds while you make your choice. So, for those of you who are able to get it, congratulations. And for those of you who just want to see the code, the answer here is D, recursion plus memoization. We won't approach the brute force approach here, We're going to just continue with the optimized solution. Now in this, we're using recursion plus memoization to efficiently calculate our minimum falling path sum. We start, and it'll show you where it is in the code here. We start from each element in the first row, recursively exploring the possible falling paths using this function, falling sum, while keeping track of the minimum sum encountered so far. And we're doing so by a combination of the falling paths function and using the min function here. By storing the results of all our subproblems within falling sum in this memoized array, we can avoid any redundant calculations and keep the overall efficiency of the solution relatively low. So let's go through this line by line. First of all, the LeetCode constraints state that the maximum size of one side of our array is 100, so we've got a constant max of 100 here. We're also initializing our memory array, a 2D array of size max, as well as this matrix, which we'll assign later. Essentially, we're going to use this and access it easily from our falling sum function. The entry point to our solution is the min falling path sum, and as you can see, it takes in our input matrix, and the first thing we're doing is assigning that to the global matrix above. After that, we're initializing our memory array with -1 values. Populating it with -1 values using memset will help us indicate that no results have been memoized for a specific row and column when we're doing calculations in our recursive function. So we'll see how that works in a moment. Once that's done, the sum variable is initialized to a very large number, int max. This is what we're going to return eventually, well, the variable sum, hopefully not int max. And you'll see how it works in a moment. Our code is iterating over the first row of our matrix from column equals 0 to cols minus 1, and each time we're making a recursive call to the falling sum function. So we're updating the sum variable with the minimum sum of falling paths starting from each column value in the first row of our matrix. So you have to imagine that we're calling from the top row from 2 and then minimizing the sum that's returned from that with a call to row 0 column 1, which is the 1 value in example 1, and then row 0 column 2, which is the 3 value. Each time we're making sure that we minimize the sum value we've obtained. So finally we'll be returning the minimum sum as the output of this function. But before we look at that, let's look at how falling sum actually works. So strictly speaking, this is a recursive function that calculates the minimum sum of a falling path from a position row column in our matrix. While we're starting with row 0 column 0, row 0 up to row 0 cols minus 1, it will be called recursively at multiple points, as you'll see below. The first thing we're doing here, and this is maybe it can be optimized for sure, we're calculating the rows and cols variables to store the number of rows and columns in our matrix. Now we've got an n by n integer array, so perhaps this can be improved upon. In any case, the next is definitely correct. This is checking whether our column index C is out of bounds or not, because as you'll recall, we'll be going down to the left and down to the right multiple times. If we go outside of the bounds, then we're going to return a very large value to indicate that this path is not valid. We're using int max divided by 2 to avoid any overflow problems. After that, we're making another check, which checks whether we've reached the final row in our matrix. If we've reached the bottom of the matrix, we're going to return the value at the current position, matrix RC, as our base case. And essentially we're going to be making sure that we add on to it, but I'll show you how in a moment. This next line is crucial in most dynamic programming problems. It's a reference variable ret, which allows us to easily access and update the value at that point in our memoized array. So memory RC. As you recall, it's populated with -1, so if no calculations have been made, it remains at that. However, if calculations have been made, it will have changed. And that's essentially what our next line checks. If the result has already been calculated, then we're going to have ret not equal to -1. So we'll have some kind of value that's been pre-calculated and stored in our memoized array. If that's the case, we're immediately going to return ret so as to avoid redundant calculations. I hope that that's clear why. If not, you're going to need to study recursion and dynamic programming in general. I will send you a link that will help you with that later on in this video. Assuming the result has not already been memoized, then our function will recursively calculate the minimum sum for the next 3 possible positions. We have diagonally left, which is given by row +1, column -1, straight down, which is again the next row down but in the same column, and diagonally right, which is in 1 row below and 1 column up. So as you can see, we now have DL, down, and DR, which make use of recursive calls to calculate those values. And to finish off this falling sum function, we've got quite an interesting line here. The result for the current position, RC, will be calculated as the sum of our current element, which is matrix RC, and the minimum of those next three positions, DL, down, and DR, and you can see how we are minimizing among them. So the result for the current position will also be memoized by storing it in the memory array. As you should remember, ret is analogous to memory RC. So it will also be returned as the output for our function, but as you'll recall, we're going to be making this call for as many columns as we have in our array. So basically n times, and then we'll be making recursive calls upon that. So that's pretty much it. This call here and minimizing among it will give us our result. And finally, the minimum sum will be returned as our output here, and it represents the minimum falling path sum through our grid. Okay, so that's it for now. If you had any trouble understanding the recursion aspect or the dynamic program aspect, I would strongly recommend checking out the link in the description to this video. Dr. Ibrahim offers a very comprehensive explanation of not only this problem, but many others, including similar problems. And practice makes perfect. If you keep at it, you will get it. Anyway, for our purposes, we're pretty much done. You should remember that you can use recursion plus memoization to solve this problem, or dynamic programming. Either's fine. And while we've got explanations as to why, we also help out by providing exemplar solutions. So we have code that will pass all test cases on LeetCode in C++, Python, and Java. So if you're having trouble just understanding the explanation, maybe you can get it by reading through the code as well. And that's it for this problem. In the next problem, we'll be continuing with the out-of-boundary paths problem. So thanks very much for watching, and I hope to see you in the next video.